Welcome, everyone. How was the motion of the ocean for you? Which is still going on, huh? So, you might find that I'm going to strap myself to this lectern, and if it flops over, the lectern and I are going down together. But be that as it may, I think the captain said things are dying out. I have a new tie for you today. See if I can come out here. I had the opportunity a year and a half ago to go to Australia on Holland America, and we had met some good friends who the husband is a retired banker and the wife is a school teacher, and I told them one of our stops is Brisbane. We were in Sydney, Brisbane, Cairns, and she said, well, let us pick you up and might you come to our school and give a lecture? And I said, sure, I'd be happy to. And these were 7th to 10th graders or so, wonderful kids, about 300 kids. And as a gift, they gave me this tie, which was designed by an Aboriginal, I guess that's the Native Americans in concept in Australia. And it's an Aboriginal tie, and I just love it, and it kind of goes with this rig, and anyway, it has an Aboriginal design. So that's today's tie. Let's talk about our Milky Way. Recall that we launched the Hubble Space Telescope in 1990 so that we could have an optical telescope above the atmosphere, and it's the atmosphere that makes stars twinkle. So if I'm above the atmosphere, I can see very clearly long distances. Hubble Space Telescope has revolutionized astronomy and cosmology because of the incredible sharpness and the long duration exposures that we have. Also, when we launched it, we had a flawed mirror, and the extraordinary team at the Goddard Space Flight Center and Johnson Space Flight Center got together and said, how can we fix this mirror when the first picture we took with Hubble looked like this? Everybody was apoplectic. I had to look that up. It means they were really disturbed, because this is what the first Hubble photo looked like. So we designed contact lenses and corrected for the error that was in the primary mirror, and then the first repair mission, and these are some pictures of it, our astronauts in the cargo bay repaired and fixed Hubble. The last lecture was the realm of the galaxies, of which there are billions, and now I want to go from this big picture and bring you back into our galaxy, which we call the Milky Way. We are inside the Milky Way, one of its spiral arms. We'll look here in a moment. When we look up at the night sky, and you have to be in very dark places, unpolluted light is the key, you will see, this is a picture, a composite picture. You can see the Milky Way as it goes across the sky, and it is not in the same plane that our sun rises and sets and our planets rise and set. There's an angle between those two planes. But this is what we see. The center of the galaxy is in the constellation Sagittarius. And our galaxy, for light to go from one side to the other, takes more than 100,000 years. Light has a specific speed. We think it's a speed limit called the speed of light. It's almost 6 with 12 zeros after it miles. 6 trillion miles light travels in 1 year. And our galaxy contains over 200 billion, that's 200 with 9 zeros after its stars. We think our Milky Way galaxy is around 13 billion years old. We think our sun, our solar system, is about 4.5 billion years old. So we are a second or third or fourth generation star that came after the Milky Way formed. Our sun is about 2/3 of the way out from the center, and our sun actually rotates around the galactic center, and it takes 250 million years for our sun to make one complete circuit, or 2/3 of the way out from the center, in a spiral arm that are rotating around the galaxy. 250 million years. That's a long, long time ago. This is the early part of the dinosaur age that it takes our sun to rotate around the Milky Way. Now let's take a look. If I were look above the Milky Way, looking down at it, I would see this type of picture. In the center, a supermassive black hole, which is the engine that drives the rotation and formation and evolution, because new stars are being formed, old stars are dying, new stars are being formed all the time, and the rotation of these spiral arms is equivalent to a hurricane on Earth, where the low pressure system in the eye of the hurricane represents the supermassive black hole. These spiral arms are density waves that would represent the arms and the thunderstorms that come out of the center of a hurricane. And so the physics of hurricane rotation and formation and thunderstorms is the same physics as stellar formation and galaxy rotation. The center of our Milky Way contains what we call a supermassive black hole, and it has the equivalent of 4 million times the mass of our sun. It is a huge, huge structure. There's a dense torus, that means a donut. There's a dense donut of gas and dust around the center of our galaxy right here, and we have multiple different stars that rotate about the center of our galaxy, and we are actually able now to measure in the last 3 decades these motion of these stars and precisely determine the location, even though we can't see inside a black hole. Black hole means light cannot escape, but we see what happens as it is swallowing and eating the dust and gas around it, heats up that gas, and it emits huge amounts of high energy X-rays and ultraviolet, and we can observe. That's what makes the brightness around the center. And we have been able to determine its mass because we have calculated the orbits of these stars around the center of the black hole. And Johannes Kepler, in the early 1600s, developed 3 laws that we still use today to put satellites in orbit, to calculate their orbit, to send them to Jupiter. They're called Kepler's laws of planetary motion in gravitational fields. The 3rd law tells us that if we know the period of this orbiting star, I can deduce the mass of the primary elements, and I can also calculate the semi-major axis, or the shape of the orbit around it. We've been doing that, so we are very confident we know the mass of this supermassive black hole and its exact location in our galaxy. We have 2 companions to our Milky Way called the Large and Small Magellanic Clouds, and they are an irregular shape or cluster of thousands and thousands of individual stars, but they are gravitationally bound to our Milky Way. They do not orbit in the plane of our Milky Way. They actually have orbits outside the plane, but our galaxy has captured them. If I go back here just very briefly, here's the Large Magellanic Cloud. Here's the Small Magellanic Cloud. We live in a spiral arm right about here, 2/3 of the way out from the center. Most of the stars orbit in this plane and the spiral arms like a record. So these companions are not in that plane. Here's our sun. I forgot to show you right there where the pointer is. Can you see it? We are in what's called the Orion Spur. And I'll show you in a moment why we call it the Orion Spur, because there's a constellation of relatively nearby stars along with our sun in this spur that makes the constellation Orion. How do we learn what elements are in these stars? And what we do is we use a spectroscope on our telescopes, and a spectroscope is like when we were in grade school, we would take light and we would put a glass prism in front of it, and out of that prism would be reflected a rainbow, right? Because the light traveling through glass, it depending on its energy, it's refracted more or less, and so white light contains all of the colors. When I put them through this prism, I spread out the colors and now can see the colors. Now, what's interesting though is most of the gas in our galaxy is hydrogen. 90% of it is hydrogen. Hydrogen has one proton in the center and one electron. When this electron is excited to a higher energy level, it can absorb energy from stars or motion. What happens is those energy levels are discrete packages of energy. They're called quantum. And from there comes quantum mechanics. This was an understanding of how atoms interact in the 1930s. We used that same mathematical concepts, and when that electron goes from a higher energy level, say 3, energy level 3 down to 2, it always emits gas, a line or a light beam, photon, light beam that is exactly this color, 656 nanometers. When it goes from 2 to 1, energy level 2 to 1, it can emit this one. So these individual electrons can emit specific light. These 4 colors represent hydrogen always, everywhere we see it, and it has this spacing between them. The color can change if this hydrogen is moving away from me. These 4 light colors will shift to a lower energy toward the red spectrum. If it's coming toward me, like hydrogen gas in Andromeda, these 4 lines will shift the other way. So I can, deduce what is the element. Each element, hydrogen, carbon, hydrogen, helium, they all have the same characteristic of a unique fingerprint of light. And that's how we can tell what are the elements that are out there. And these 4 lines are called the Balmer series. And they're very, very powerful for us to gather information about other stars and other galaxies. Now, there are 2 different ways that we can see this. If the hydrogen is emitting these colors, it looks like this, a black background with the colors. If the object of interest is absorbing energy, what happens is these same 4 lines are black. And here's our spectrum of light from that far distant star. This is called a hydrogen absorption spectrum, a hydrogen emission spectrum. Don't worry about taking notes. This is not on the pop quiz. I'm only trying to tell you that there is a way that we can tell from quantum mechanics and how protons and electrons act, what are the elements in the atmosphere of any star that we can see. Now, let's stop all the science and start looking at some beauty. How many recognize this constellation? Anybody? The 7 Sisters or the Pleiades. We have been observing the Pleiades since we learned to write down history about 6,000 years ago. Here's an example in the Old Testament, Job 38:31. Can you bind the chains of the Pleiades? This was probably written about 2000 BC. And what it is, it's a magnificent open star cluster. This cluster is bound together. In other words, these many stars are a group. The gases that you see are basically hydrogen, and the star within that cloud of gas from which this star collapsed and formed, and like a flashlight turned on, there's still gas outside of it, and it is emitting light that is exciting these hydrogen atoms, and they are sending me that emission spectrum that I showed you earlier. It's a beautiful, you can see it with the naked eye. You have to be in a very dark area. It is in the constellation Taurus, and I hope, I don't know whether it's up this time of year. It probably is up around 3 a.m., so it's not likely you'll find me up on the aft deck pointing this one out. But the beautiful Pleiades, another famous constellation. Anybody heard of this one? Orion. In the fall, Orion is one of our very wonderful, very bright, and this is a picture. Notice what these three stars are the belt of Orion, right? The sword of Orion is hanging down. This one right here where my arrow is called the Great Nebula of Orion. Is a huge cloud of dust where new stars are forming all the time. I'm going to blow that up for you and show you some extraordinary detail we've just discovered in the last decade or so. But notice the other thing about stars is they have different color, right? We classify stars by color and brightness. This is a supergiant reddish star called Betelgeuse. If it were in the center of our solar system, its surface would reach halfway between Earth and Mars. So there will be no Earth-like planet 93 million miles from this star because it would be plasma or a gas. It's so hot. This is about 4,500 degrees at the surface temperature of this star. Red stars are cooler. They live longer than very bright stars. This is called Rigel. Also a blue giant, and notice the color difference. The color tells us that the surface of this star is much hotter than Betelgeuse, and in fact, it's 3 times hotter. It's about 18,000 degrees centigrade. They burn their fuel at prodigious rates, and their lifetime is a fraction of the lifetime here. When they burn up their fuel, they're fusing hydrogen into helium, helium into carbon, carbon into oxygen, oxygen into the other elements. When you get to iron, which is element number 56, that fusion process stops, and we no longer get energy out that keeps the star from collapsing, and that energy out stops. The inner core collapses almost instantaneously, and the star explodes and spews out all of the heavier elements that come after iron are formed in a supernova stellar explosion, like a dandelion that at the end of its life is sending its seeds out into the universe. Our star, our sun, every element that is heavier than iron came from some explosion of a supernova in our galaxy long before our star formed, and that's why we have heavier elements than iron. Those heavier elements are formed in the outer layers in the instant of that explosion and sent out into the Milky Way, and later collapse and become second and third generation stars. The iron in your and my blood was formed in the core of one of these stars billions and billions of years ago. So Rigel burns quickly, very hot. I want to tell you one other interesting thing. Those of you who have been to Egypt, have you seen the 3 pyramids on the Giza plain outside of Cairo? Anybody been there? The Egyptians worshipped the constellation Orion, and these 3 stars are exactly the angular or the alignment of the 3 pyramids. This is Cheops's pyramid. This is his son's pyramid in a line, both similar size, so similar brightness. This is the grandson's pyramid, slightly offline with the line of the first two, and they have reproduced on the plains of Giza outside of Egypt this exact picture with 3 giant pyramids. Pretty extraordinary. Rigel is 40,000 times brighter than our sun. It's 800 light years away from us, so if it blinked out right now, we wouldn't know it for 800 years. Its energy in the ultraviolet is so powerful that 40 light years away is what we call the Witch Head Nebula, and Rigel's energy is what is causing this hydrogen gas. It's electrons to be excited, and as they unexcite themselves, if you will, they send out this light of the beautiful Witch Head Nebula. This is a Hubble photo. Let's go to the Great Nebula of Orion. That's going back this fuzzy place right here. Beautiful. If you've got binoculars, look at that. It's quite an amazing sight. You don't need giant telescopes. This is a visual. It's a stellar nursery of thousands and thousands of new stars, including new planets or protoplanetary disks being formed as we speak at the very moment, right now. There are violent jets and supersonic stellar waves that are blasting away from this new stellar formation. There are 4 stars in the center, very young, very hot, very energetic. It's called the trapezium, and they are in the shape of a trapezoid, and they're right here, and everything that you see that is glowing comes from the light of these very energetic 4 young stars, causing all of this dust and gas, which is swirling and changing, and new stars collapsing out of them all of the time. It's incredible, beautiful. This is visible light. This is what our eyes would see if we could look using photograph from the Hubble Space Telescope. What we do, though, is we like other pieces of information, so we can use infrared, which is below what our eyes can see, and we can gather more information. This is a composite of visible light and infrared light from the Spitzer telescope, and look at the highlight here that represents oxygen. There's a high concentration for some reason of oxygen in this turquoise area, so we can learn a lot from the colors of this light. Now what I'm going to do is go to a specific area and blow it up with Hubble. I'm looking at this object right here, and I blow it up again. That is a new star that has formed, and there's a violent flow of gas coming from this direction, follow my arrow, that strikes the outer magnetic field of this star and forms a supersonic shock wave as it goes around this star. We see that throughout the Orion Nebula. Here's another example, and this is in a different place, so the energy that's blowing this gas past the star, in this case, is coming from a different direction. But we call that a bow shock. Inside, we're blowing it up again. The Hubble, this is called, you realize, of course, that NASA and all of us folks have our own language, right? We call them acronyms. So you're probably sitting there dying to know, what does WFPIC-2 mean? Right? WFPIC-2. It means Wide Field Planetary Camera, 2nd generation, that we took up on a repair mission, and we took these extraordinary photographs. What you see here is a star with dust and gas around it called a protoplanetary disk. It is now forming planets around these stars that are changing and evolving inside the Great Nebula of Orion right now. Down in the Atacama Desert in Chile is what's called the ALMA, which is a magnificent ground-based telescope. This is in November of 2014, we took this picture of a star. It's 450 light years away, And what you're seeing with that ground-based telescope now, which we have made extraordinary advances in being able to cancel out the atmospheric twinkle. And now our ground-based telescopes can take pictures as clear and as powerful as the Hubble Space Telescope. And this one is showing that there's clear lanes of dust. There are planets forming in HL Tau right now at these various distances from this star. That's from the Atacama Desert and the ALMA telescope. The Tarantula Nebula. Look at all of the stellar formation and the magnificent structure. There are silicon, oxygen, hydrogen, helium, dust, gas, all of the stuff that we basically have on Earth is in this area, and it is has a lot of stellar formation going on right now. It's a very active region. It is in the Large Magellanic Cloud. We have actually seen our first supernova, the explosion of a star 20 to 30 times more massive than our sun, since the telescope was developed in the 1600s by Galileo, and we were able to measure that in 1987 in this nebula. It was close enough to us to give us a tremendous new information and picture and understanding of what happens when stars explode and how they make these elements. The beautiful Roseate Nebula. We did not understand until I'd say the 1960s, 1970s, how these could form. What happens is a large star right there where my pointer is has exploded. It has pushed away its outer layers. When this star exploded, there are about 4 different forms of stable matter that this star can exist. Our star is one where it's doing hydrogen fusion. The next one is I collapse the electrons. This is maybe too much information, but electrons only can be one electron, and another electron cannot be in the same energy state. But I can collapse them from gravity and make what's called, our sun can be collapsed into what's called a white dwarf. It's still normal matter, but every electron is at its Fermi level, its lowest possible level that it can be, and something as large as our sun can be collapsed to about the size of Jupiter. Okay? And it will stay stable that way for long periods of time. A much larger star that explodes, when it explodes, it actually drives the electrons into the protons and forms a neutron star, which is another stable point. They are something the size of our sun collapsed to the size of the Earth. Incredibly powerful gravitational fields. A teaspoon of this stuff would weigh more than this ship, and more than 50 of these ships probably. It is incredibly powerful. They have a unique characteristic, and I want you to, I'm going to do a little physics lesson here for you. What happens to a skater when they start their spin and they bring their arms in? What happens to their spin rate? They go faster. It's called conservation of angular momentum. When this sun or this star exploded, it is rotating. So when it collapses from the size of the sun to the size of the Earth, what happens to its rotation rate? Much faster. So our sun rotates once in 28 days, give or take, a little different at the poles than in the equator. Now, if it collapsed into a neutron star, it would be spinning at 30 times a second instead of once a month. And what happens is we have observed these, we understand the physics, and we have found stars called pulsars, and they are basically a flashlight or a lighthouse in the sky, and its rotation axis happens to be pointed at Earth, and we see this star with our eyes, and it's blinking 30 times a second. It actually can blink at different rates, and we can measure those. I'm going to come back to that at the end of this lecture. Why am I telling you this? Because it has a unique signature. It has a unique place in space, in our galaxy, and we are trying to tell people who might find a spacecraft that we sent where we might have sent it from. We'll come back. So these are the outer layers. It's glowing beautiful red. That's one of the hydrogen-specific lines, excited by the pulsar neutron star in the center. There are millions of these. If you were here for the first one, remember I told you we had to have a standard candle to measure distances. It was a Cepheid variable. This is one in the southern hemisphere, a Cepheid variable. They are a star whose outer layers are expanding and contracting, and it can be days, weeks, or months. And as they expand, they get brighter. As they contract, they get dimmer, and because of the surface area. And we use that information to deduce distance. You'll have to join me at a table for hosting, and I'll explain that if you're even slightly curious. And if you just want to blow that off, just accept that we can tell distance by understanding the period of this star. This is a beautiful Hubble photo where its light is echoing out through the gases surrounding it and making this beautiful, beautiful structure and picture as that light propagates out through the gas. The Ring Nebula, beautiful, another pulsar right in the middle. Can you see it where my pointer is? It is almost 1 light year, 6 trillion miles from here to here. Look at also the outer layers, the structure that we see with the Hubble Space Telescope and long time exposures that says these explosive events have multiple different cycles and events that happen at different times and different speeds, and these layers are expanding away from this pulsar at different times and speeds. The beautiful, why do you think we call it a butterfly nebula? They have fancy names. Its fancy name is NGC 6302, but who's going to remember that? So we call it the Butterfly Nebula, and even I can remember that. What's interesting is look at the symmetry. There's an exploded star right in the center, also a pulsar, a neutron star, but its rotation axis is right here. See where my pointer's going? That's the north and south pole of this pulsar that's rotating. Its magnetic field was so powerful that it shaped the direction of these gases as it exploded. Every one of these exploding stars has a different shape, a different signature. Every one is absolutely unique, and most of them are incredibly beautiful, as you can see. I'm going to talk about the Eagle Nebula. That's called M16, 7,000 years away, but look at how extensive. This is a large area of the sky. A Hubble photo, most of this red is hydrogen gas, and I'm going to blow up these two areas of the gas, and let's see what's happening in these two areas. The darker colors are generally dust and silicone, and they're not hydrogen and helium. This is the fairy of the Eagle Nebula, which I want to show you, if I go back, is this structure right here. Now I'm blowing it up. Look at this incredible detail. There are carbon, silicone compounds, dust and gas that are the dark colors, and we are seeing new star formation. This star right here formed at the end of this finger of dust and gas, and it's collapsed and turned into a new star. So there are new stars blinking on all of the time. Now and it takes light from this new star to go to here 10 years, 10 light years. Similar thing, the gaseous pillars. These are called sometimes the pillars of Hercules. They stand 7 light years from here to here, and you can see new stars, there's one right there, being formed in the denser gas. It collapses upon itself and makes a new star. Another example, the Cone Nebula. These are new stars that have formed in the density. Think of this as like, how many of you have lava lamps? Or probably our kids had lava lamps. Remember that stuff that's bubbling up in the lava lamp? That's what's happening with this gas that's bubbling up here, and it's changing, and it'll reach a point where the density is just right, and now gravity will take over and make a new star. The Cygnus Loop, beautiful veil curtain of dust and gas. Here, I showed you this picture earlier from 1995. Look at how important it is to build a spacecraft that can take advantage of the new technologies that we're able to develop if we can go back and visit them. This was our best camera in 1995. This is the third generation wide field planetary, and we took this picture, same thing, 2014. Look at the incredible increase in detail and structure from the new camera. The beautiful Horsehead Nebula, this is just below Orion's belt. You can see why we call it the Horsehead Nebula. And here's a blow up of the Horsehead. New stars, there's a new one being formed. And this gas is turbulent, it's moving and it's changing. If we were here 1,000 years from now and took another photo and overlaid it with this one, we would see that gas moving and that structure. It's just much, much longer than human lifetimes. And a dramatic new 2013, this is the Horsehead Nebula right here, now looking in infrared light, which tells us a lot more. We can see through some dust and gas with infrared light, and look at the incredible structure of this boiling columns of gas and dust out in our Milky Way. This is not out in the far universe from the last lecture. This is in Orion's belt. Another beautiful cluster and star formation region. Stars like to form in clusters. The light from these newly formed stars, newly is a relative term, by the way. Some of these can be 1 billion years old, but look how it is exciting and pushing away and changing the structure of this gas where new stars will form. The Little Ghost Nebula, another pulsar neutron star right there. It's a dying star. You can see how it's had different events and different colors, different elements, in fact, in these rings that surround it. A couple quick examples. Planetary Nebula. Love this one, brand new. This is the same M29 Planetary Nebula, and there are large areas of high energy radio waves coming from these two lobes. Now look at the new image from Hubble. Incredible structure and detail. Love this one, Cat's Eye Nebula. That's X-rays. Here's what it looks like in visible light, sometimes called the Eye of God or the Cat's Eye Nebula. And look at the incredible complexity of this explosion as it changed and expanded over a period of time. Another example, the hourglass. I believe the Chinese must have seen this to invent fireworks, because that's what we see on 4th of July, right? Eskimo Nebula. Every one of these is unique. There's a pulsar, the neutron star, right in the center. You can now flip through this quickly. This is just a collection of, notice the color, structure, shape. Every one is different and unique. Monocerotis, changed over time, May 2002, September, October, December. That's the light echo of some event on this pulsar that is now echoing out through the gases, and it had some probably surface explosion or something. Cassiopeia was a supernova pulsar right there. No mention of this in 1666 in any European written records. The Crab Nebula, another example, the pulsar right here. Interestingly enough, this exploded in 1054 AD. It was so bright you would see it in broad daylight. This star becomes so bright for a month that it would be brighter than Venus. You could see it in daylight. We have found written records in Japan, China, North Korea, and Native Americans saw this star, plotted its position. There's absolutely no mention of it in any European book or history that we found. And I've often wondered if maybe they called it the Dark Ages in Europe because nobody looked up. Beautiful composite. Here's looking for oxygen and sulfur with two different types. And you notice that it changes the shape and brightness of the filaments as we look in these different wavelengths of light. Another beautiful supernova. This one is 1987A that I mentioned in the Large Magellanic Cloud. Now Hubble is looking at it, and since 1987, it has this ring of diamonds like a tennis bracelet around the explosion since 1987. This is what we see now. This is the first plaque that we sent on the first probe to actually leave our solar system. It was on Pioneer 10 and 11. Carl Sagan was involved with a team of people that put together, they tried to say, if someone finds this probe, they made a movie similar to this called Voyager. It was one of the Star Trek 1 movie, I think, Voyager, only this is Pioneer. We were trying to say, what information could we give someone that says, where did this come from? What's our measuring stick? What do we look like? Now, if you're young and impressionable, close your eyes for a moment. They must have had a 2-week meeting to decide whether we put fig leaves on these two people right here. And what we're trying to do is say, I come in peace. My right hand does not have a weapon, is extended in peace. I am two species, male and female. My height is equal to, here's the spacecraft. And so if I stood next to the spacecraft, this is how big we would be. Then we went, if you knew where our star was, we live on the third rock from the sun, and we swung by Jupiter and increased our speed so much by stealing a little bit of Jupiter's angular momentum. We actually slowed down Jupiter very slightly when our spacecraft went by and slingshot away, that in maybe 10,000 years, we might be able to measure that Jupiter is 1 millimeter behind where it should have been if we hadn't swung the spacecraft by. We didn't really hurt Jupiter's orbit very much, but we did steal some of its energy. So the spacecraft went around Jupiter. Then I have to provide them a yardstick. This is a hydrogen atom. It has a very unique wavelength of radio wave. It is exactly 21 centimeters. That's about 9 inches from here to here. That's the wavelength of a radio wave that is emitted by hydrogen, which is 90% of the universe. When this electron goes from spin up to spin down, it gives off a radio wave at 21 centimeters. Anybody who's smart enough to capture this telescope will know that that represents spin up, spin down, 21 centimeter wavelength of light. So now we've given them a yardstick that they can measure. And right here is the sun with all of those nearby pulsars, neutron stars, and in binary code. Do you think these people will speak binary if they can capture our satellite? What do we use binary for in modern day use? Anybody? Computers. It's either on or it's off, right? So we have encoded on this line what's the spin rate, what's its direction, and how far, using this yardstick, is that pulsar away from here, which represents our sun. Incredible stuff. And that's my last slide for you. And Ian Fleming, right? James Bond. Ian has a lecture at 3:30, so I have time for maybe 2 questions. Let's do one over here. Anybody? No questions. I dazzled you so much you have no questions. Okay, right here.
Hey, do you do your lesson on physics? You want to connect it to at the end of your lecture?
Do what, sir?
Your lesson on physics.
My lesson on
You want
physics.
to connect it to something else?
You'll have to come to University of Colorado. I'll be teaching that this summer.
Okay.
But I'm sorry, I didn't mean to make fun, Alan. What? What?
You say we're giving a lesson on physics before when you showed we demonstrated something physical.
Okay, so I'm giving a lesson on physics. It's because I'm a closet teacher, and I just can't help it.
You're going to connect it at the end of your lecture.
Oh, am I going to connect it? I was trying to connect it in this lecture by teaching you about angular momentum and skaters, and that's why exploding stars who keep their spin rate are going so fast. But after dinner, I'd love to do that for you, or join us at dinner. Yes, sir.
You talked about turbulence and gas.
Yes.
I thought turbulence had to have some kind of medium for turbulent in.
The medium is the gas and dust itself. So consider it like a gaseous sort of liquid, if you will, and it's not homogeneous. It has different levels of density and elements inside of it. What's causing it to move is the energy from nearby stars, high energy, ultraviolet, and other, that is exciting it and it's sort of like the lava lamp where I've got low heat and I've got convection currents inside of it. One last question right here. Yes, sir.
We can record the light. What about sound? Do we know what it sounds like?
Do we know what it's like?
What it sounds like?
What it sounds like. You know, actually people have done, you could Google sounds of a star, for example, and they have taken, there are sounds, even to our sun. As those turbulences happening up there, it can give off the equivalent of sound waves. Now, and they've actually have some records or examples of what that might sound like. It's not really a true sound wave because sound requires some medium to propagate, correct? And in between the sun and us is almost nothing. You know, maybe one atom per this size, per basketball. So hope you have a great time. The next lecture, we're going to go from Milky Way and we're going to come inside our solar system. I'll include some new findings of water on Mars, for example, different forms of water, and also some new photographs of Pluto, which we sent a probe and it took 10 years to get there. The probe is still sending us new photographs. It's so far away. It's millions and millions of miles past Pluto. It flew by Pluto like a supersonic bullet. But we stored that information, and now we're sending it back one photograph at a time. It's so much data, and it's so far away that we can't just dump it all at the same time. It will be doing that for several years yet. So have a great time, and see you next time.